Hi guys, and welcome to our video on the periodic table. We're going to start out with a little bit of history of the periodic table, just to kind of lead you through where it came from, and then we're going to talk about some common trends and things you can find out just by looking at the periodic table, which is really cool. But let's go way back. Guy with the coolest name in science, Dmitri Mendeleev. Maybe not the coolest name, but it's up there. Dmitri Mendeleev was a Russian chemist and an inventor, and we consider him the father of the periodic table. He is the starter of this whole thing. In the 1860s, he was a popular lecturer at a university in St. Petersburg, Russia, and he was, of course, lecturing in chemistry. And since there were no modern organic chemistry textbooks in Russian at that time, he figured why not write one? And while he was writing it, he decided to tackle the problem of the disordered elements. See, at the time, they had a bunch of elements around, nobody had, and they just were in a book somewhere. Like you just look up the element that you might have been working with. They had no order, no reason to rhyme. They're all over the place. There's got to be some kind of system to organize these with. This is my man Mendeleev right there, looking sharp. So what he did to help organize himself is he wrote the elements down on cards. So he'd take a card and he'd say, okay, let's say this is hydrogen. What do I know about hydrogen? And so he would write the weight of hydrogen, and he'd write what it reacts with, and he would write whether it's an acid or a base, and he'd write what its density is, and he'd write everything he could possibly think of. He had all these cards with all the properties on them. And so he tried to rearrange them all kinds of different ways. They said he was playing solitaire with these cards. And eventually he began ordering them by increasing atomic weight. So there's a little weight number in the top corner. He's like, I wonder if I could organize them by weight, and let's see what happens. So he puts them all in order by weight. And he noticed certain types of elements regularly appearing. He's like, what's happening here? It seems like every 8 or so, I get the same type of element showing, one that acts the same way. So for example, he knew that lithium and sodium and potassium all acted very similarly to each other, and they were exactly a certain range, a certain number of elements apart. So when he put them in line, it was 1, 2, 3, 4, 5, 6, and then sodium. 1, 2, 3, 4, 5, 6, and then potassium. And he noticed that same pattern several times. So he's like, okay, there's something here. There's some kind of trend around elements that act similarly and their weights. So he worked intensely on this puzzle, he called it, for 3 days, just nonstop, just trying to figure out these elements over and over and over. And when you spend that much time on something, well, you start to dream about it. And Mendeleev said he actually ended up dreaming about these elements, and they all just fell into place. In his dream, he pictured this table of elements that just worked. So he woke up and immediately started writing things down on a scrap of paper, and he comes up with something that looks kind of like this. So this is crazy, complicated ordering of things, but he says, okay, anything in a row here, in a column, seems to act fairly similarly. So I'm going to put the families together. And then look at this. It still goes by weight. 1, then 6, 9, 10, 12, 14, 16, 19, 23, 24, 27. They're all going according to weight. And so this is it. This is the table. This is where all the elements should be. Fantastic. Only in one place did he find a correction that seemed necessary, where a weight didn't quite line up with what he was expecting to see. So look at tellurium and iodine here. So tellurium is heavier, but iodine definitely belongs in this family because of the way it acts. So I'm going to have to switch these. So he arranged all these elements according to both atomic weight and their valence electrons. Now, I don't know if he knew it was valence electrons at the time, but that's what he was organizing them by. How many electrons they had in their outside shell. Now, the interesting thing is, as he kept organizing and kept revising this table, so this is his same table, he just updated it a bit, did a little more organizing, made it look nicer. Not only did he leave space for elements not yet discovered, if you take a look here, he says there's a blank here. There should be something between 65 and 72 that has the same properties as aluminum. Just, he's looking at the weights and looking at how the things react. There's a blank in my table that needs to be filled. And he said, I bet you there's an element that no one's discovered yet. So he left a space there and said, hey guys, go look. There's going to be something that weighs 68 that's similar to aluminum. Go find it for me. And not only did he say, go find it for me, but he predicted their properties. He said, look, it's in the same family as aluminum, so you're going to expect this kind of melting point, this kind of boiling point. It should be metallic. It should be shiny. It should have this density. And everyone laughed at him. They're like, there's no possible way your table is going to predict elements and their properties. You can't know what something we've never found will look like just by this crazy table of things. But then they went looking and found them. And so Mendeleev was very much on his high horse. He's like, yep, you found my elements and they matched really well. I'm doing awesome. But compared to the rest of his work, Mendeleev's list actually misplaced 7 known elements: indium, thorium, and the 5 rare earth metals, yttrium, cerium, lanthanum, erbium, and didymium. And the latter 2 are actually later found to not even be elements. They're mixtures of different elements. Those didn't match the pattern of reactivity when he put them according to atomic weight. So there was a number of weights that just didn't fit. So if he put them where they belonged according to weight, his table didn't work. And so in early 1870, after his success predicting elements, he thought, I think he was a little full of himself. So in the early 1870s, he said, all right, well, it's not my table that's wrong. It's the weights of the elements that must be wrong. Go back, reweigh these elements, these 7 elements. The weights must not be right because they don't fit my table. Now, we know now this is not the case. His table was close, and it was very accurate, but it wasn't totally correct. And so the reason it didn't match was not because the weights were wrong. Oops. It was because he was wrong. So a number of years later, a Dutch guy, an amateur Dutch physicist, Antonius van den Broek, was the first to propose that maybe it's not weight. Maybe it's atomic number. Now, the reason it took 20 years is because they had no idea about protons yet. It took a while to get those discovered and all that stuff sorted out. So once they figured out atomic number, Van den Broek said, well, maybe it's atomic number, actually. Maybe it's how many positives are in the nucleus, what the nuclear charge is. So maybe that's what's supposed to determine the placement of elements in the periodic table. But again, things were new, and so it was kind of hard to measure how many protons there were. He correctly determined the atomic number of all elements up to 50, which is not that impressive when you think about the 118 elements we now have. And he made several errors in the heavier elements, which means the table he's trying to build is actually not that good. It doesn't match up at all because he's making all these mistakes. Also, look at this guy. Super dapper. Apparently all you need to be a good-looking scientist is to work on the periodic table. And again, Mr. Moseley, sharp-looking dude, he comes along afterwards, Henry Moseley, and he says, you know what? I think you're onto something. I just don't think you did it right. And so he starts accurately measuring atomic numbers. And he determined the absolute sequence to the elements. He figured out that no, Van den Broek was actually right. It is atomic number. It is not atomic mass. So he restructures this periodic table. He redesigns it into the modern shape we have today based on atomic number. Moseley's research immediately fixed all the differences between atomic weight and chemical properties. All those times where the weight didn't line up with the properties, it was totally fine when you arranged it by atomic number. It just solved it. Instantly, everything fit perfectly. And so that was it. That was the key. Everyone's like, oh, I guess we got it. Moseley's thing works. It resolves all the issues. Everything is in its place. All the families have similar properties. If you look down a column, and they're all arranged by atomic number. There's no mass differences, no switches. I think we're good. And so Moseley is widely credited with basically coming up with our modern concept of the periodic table. So now that we've got a periodic table that works, the one you're looking at the wall is actually Moseley's version, or very similar to it. It's got new elements now that we've discovered recently, but periodic table trends. What can we use this thing for? Well, the periodic table, we already know it arranges all of the known elements in some kind of an array, and it tells us a lot. Elements are arranged from left to right and top to bottom in order of increasing atomic number, as we just said, thanks to Moseley. And as you increase, it generally coincides with increasing mass, because protons weigh 1, right? So as you increase the number of protons, you increase the atomic mass. So generally speaking, that's why Mendeleev's was so close. It's almost a perfect match. There are a few that have too many neutrons. Well, I shouldn't say too many. They just have more than you would expect, and that throws the mass thing off, but it's not super common. So remember, protons and neutrons all in our nucleus, right? And little electrons, which don't weigh enough, zipping around the outside. So here's our periodic table. If you take a look carefully examine it for a while, you'd find that, yeah, mass almost always increases. Pretty much across the board, wherever you're going, you're going to see mass increases. There are a few cases where it's not true, and they flip. If you really look, you can find a few in there, but it's not like super common. And so atomic number, though, atomic number 1, atomic number 2, 3, 4, 5, 6, 7, 8, 9, 10. It always goes up by atomic number. And so we've discovered every element from atomic number 1 all the way up to number 118. And this periodic table is slightly out of date. These crazy ones down here a lot of them have been named already. You can Google that if you're interested. The naming of these crazy elements has a cool story behind them. And so we have special names for the rows and the columns. The rows are called periods. You can see it's there in tiny writing, but I'll write it big. So each row is called a period. So period 1, period 2. The period number of an element signifies the highest energy level or the highest orbit an electron in that element would occupy. And so the number of electrons has to increase as one moves down the periodic table. So if you think about it, this one could have anything in period 1 has less electrons and stuff in period 2, which has less electrons and stuff in period 3 because they're increasing the number of orbits. If you guys remember your Bohr diagram stuff, you remember that, oh yeah, that's how many shells you've got, how many orbits, how many circles around that I can put electrons in. So that's what the period number tells us, how big the electron is. As I go down, my atom gets bigger because I'm increasing shells, I'm increasing distance from nucleus, I'm making things bigger and bigger and bigger. Elements that occupy the same column on the periodic table, which is called a group. So this is group 1, this is group 2, and for chemistry, we usually call this group 3. It's not technically group 3, this is technically group 3, but because there's a huge gap in here, we tend to skip over it because we don't look at the elements that are way down here until much later in chemistry. For now, consider this section over here to be group 3. It'll make your life a little easier when trying to conceptualize chemistry. Technically, it is group 13, but a lot of times we think about it kind of as group 3. And then, of course, you've got 4, 5, 6, 7, and 8. So these groups, why do we care? Well, they have identical valence electron configurations. Now, what that means in English is they have the same number of electrons in their outside shell. Group 1 has 1 electron in its outside shell. Group 2 has 2 electrons in its outside shell. Excuse me, group 13, or group 3, is 3 electrons in its outside shell. 4 electrons, 5, 6, 7, and of course 8 electrons in its outside shell. So the group number tells you how many electrons are in the outside shell. And why do we care? Well, the valence electrons tell you how they react. And so if they have the same number of valence electrons, they behave in a similar way chemically. They'll react with the same thing. So for example, all the group 18 elements are inert gases. So helium, as you probably know, you can breathe that in, right? Makes your voice all squeaky. Doesn't hurt you, doesn't burn you. It's not flammable. It's not poisonous. It's not toxic. Guess what? Neon's the same thing. You could breathe it in if you wanted. Wouldn't be toxic, wouldn't be flammable, wouldn't be explosive. Argon, krypton, xenon, all of these, not toxic, not flammable. I mean, radon's a little radioactive, so you don't want to breathe that one in just because it gets so big that it starts to be give off radiation. But all the rest of these are the exact same in terms of their danger to you. There isn't none. They're super stable. But if you go over one group, you would want to run kicking and screaming as fast as possible away from anything in this family. Do not put it anywhere near your body or you die very quickly and very painfully. We'll talk about why in just a second. So if you look at group 1, I just whipped up some badly done Bohr models, but you can see lithium is in group 1. There's its 1 valence electron. Sodium's in group 1. Even though it has an extra shell, it's only got 1 electron in its outside orbit. So they're both single, we say these both have 1 valence electron, which means they would react very similarly. Anything that sodium reacts with, you would expect lithium to react with. So why? Why do elements with the same number of valence electrons actually act similarly? Why does that matter? Well, this is super important, guys. This is basically the foundation of the vast majority of chemistry that you do. So pay real good attention to this. The outside electron thing, the valence electron thing, super important. And here's why. All elements are trying to do the same thing. They want a full or empty outside shell, outside orbit. So if I have one electron, we want to get rid of it. I want to get to 0. If I have 7 electrons, I want to find one more. I want to get to 8. That's going to make me happy. Now we call this the Octet Rule because most of the orbits in the first few periods hold 8 electrons. We zip back to our periodic table here. You can see that this row holds 8 and this row holds 8. And so all of those elements are trying to get to 8 or 0 in their outside shell. The first shell technically only holds 2, but there's only 2 elements there. So we're like, eh. And again, the bottom ones can hold more than 8, but we don't worry about the bottom ones yet. Those are for more complicated chemistry classes. For now, we're going to look at the top 3 periods only, and they're always trying to get to 8. And they're the elements that are most widely known, and so that's where the Octet Rule name came from. Let's get back there, Octet Rule. So most of those orbits in the first few periods hold 8 electrons. That's what we want. If I get rid of all my electrons, I've got 8 in the shell behind me. Or I can gain a few and get 8 in my current shell. So let's look at the group 1 metals. All the group 1 metals, sodium, lithium, all those ones in group 1, they have 1 valence electron, which means they all want to lose 1 electron. That would help them empty their shell. I mean, the other option is gain 7. And if you think about it, what's easier, getting rid of one thing or gaining 7 more, right? It's just a numbers game. They're almost always going to lose 1. In fact, getting them to gain 7 would be crazy difficult because they want to lose that 1 so badly. Now, this means that they all act similarly to each other. They're all trying to give away a single electron. They will all pair with anything that could take a single electron, which means they're going to pair with the same kinds of chemicals. So they react with similar things. And now, how reactive something is depends on how close an element is to having a full or empty shell. The closer it is, the more reactive it is. If you think about it like, I don't know, a lottery ticket. You've scratched 6 numbers and they're all right so far. You've got 1 left. How desperate are you to have that last number be a perfect match, right? You're going to lose it. You would kill to have that last number be a perfect match, right? I want it. I need it. That's how these elements are. If they are 1 electron away, they are going to do whatever it takes to get that electron. So anything that is 1 electron away is scary. And that 1 electron can either be, I need 1 electron, or I'm going to give away. So this is group 1. I want to give away 1 electron. Those would be very reactive and very scary. I want to steal 1 electron would be very reactive and very scary. Either of these are going to do whatever they can to get rid of their electrons and be very dangerous. If you move over 1, let's look at group 2 here. They're like, okay, I got 2 to get rid of. So this is like you got your lottery ticket. 5 numbers are a match. That's really good, but like you got 2 left. The odds aren't that great. So they're going to be fairly reactive, but not nearly as scary. Same with these ones here. Fairly reactive, but not that scary. You say, wait a second, oxygen. Oxygen? Really? We breathe that. It can't be that reactive. Pure oxygen is actually pretty dangerous. The air we breathe is like 20% oxygen. It's only 1/5 of what you breathe is oxygen. If you concentrate it, it's actually poisonous, which is kind of crazy. But as you get to these ones here in the middle, boron is like, well, I could lose 3 or I could gain 5. Carbon, gain 4, lose 4. They're like, like, it's like you got your lottery ticket, you scratched it, you got the first number. Cool, I got 1 number. Who cares, right? Like, I got the rest of the ticket to scratch. It might not turn out. So they're not going to be nearly as reactive. Where are we at? There we at. So the harder it is for them to get their full or empty shell, so if they're halfway between full and empty, they're just not as reactive. They're a lot safer to handle. So for example, sodium versus carbon. Sodium is group 1. Carbon is group 4. If I were to look at its outside shell, sodium has 1. Carbon has 4. How do they get to 8? Well, group 1 is obvious. Lose it. Lose 1. So is it going to be reactive? Very reactive. If If I look at carbon, I could gain 4. That would get me to 8. Or I could lose 4 electrons. That would get me to 0. Both are good. But I mean, that's a lot of work, gaining 4 or losing 4. So it is probably going to be barely reactive. Now, carbon, if you didn't know, it's like ash or coal or diamond, right? You can hold on to carbon or ash in your hand, and it's not going to cause you any problems. You can throw it in water. It just sits there. It's basically like a rock, right? It is literally as inactive as a rock. If we have sodium, on the other hand, well, let's take a look, shall we? Title of this video, Don't Flush Sodium Down the Toilet.
This is a solid chunk of sodium metal. This stuff is number 11 on the periodic table of elements, and it is extremely reactive if it comes in contact with water.
So there's the hint. Let's take a look.
It's just a long piece of PVC pipe so we can flush the toilet from about 10 feet away. He's going to drop this into the toilet bowl. We're going to let it fizz around for a bit, and then we're going to flush it and see what happens. Here we go.
Doesn't look like carbon to me.
I can hear it crackling and fizzing. All right, flush it. Okay, here we go. Whoa!
So you can see as the water comes into contact with it, boom! It gives away that electron so fast.
That's what you call explosive experience on the toilet.
You get an explosive experience. This is the biggest
chunk of sodium I've ever thrown into water, so a little bit nervous about this one. We're definitely flushing this from a distance. And I think I'm gonna actually have Cody throw it in this time. Go for the swoosh.
Didn't even get a chance to
flush it. That reaction actually was pretty cool. That was fun. This time we're gonna do the same thing. We're gonna flush it and see if we can make it go off during the flushing process. I'm wondering if we should go a little bit bigger just to take it to the next level. This is the grand finale. We got a whole handful of sodium here, like 6 chunks. I'm gonna throw them in, and at that exact moment, Cody's gonna flush, and hopefully we'll get some kind of
Notice he's wearing
reaction.
gloves.
You ready for this?
So that's sodium just in water. A little bit terrifying. And by a little bit terrifying, I mean very terrifying. You don't mess with the group 1 stuff. But some people always ask me, okay, but like sodium, like the sodium we eat, like salt? So I'll give you a little crash course secret on what this is going on here. Sodium has 1 electron in the outside shell. Salt is sodium chloride. Chlorine, if we check our table, chlorine is one of our terrifying ones over in group 7. It has 7 electrons in the outside shell. So how many does chlorine want? Well, it wants 1 more. How many does sodium want? It wants to give 1 away. You put these 2 together, that explosion is going to be way bigger than the toilet explosion. But what ends up happening is sodium gives the electron away. Now sodium has 0. It's happy. Chlorine now has 8. And they're stuck together because they've shared electrons. So chlorine now has 8. It's happy. So if you take sodium chloride, if you take table salt, well, the sodium's happy now, the chlorine's happy now. Neither of them wants to give away or take electrons because now they've combined. And so sodium chloride itself, super stable and super safe because 2 very reactive things have already reacted. So that's why it's so important to know this chemistry. Some people say like, oh, that thing is super dangerous. Well, maybe on its own it is. But if you put it in a compound, it totally changes how it acts. So we're not going to look very much at compounds this year. This is not really what we're going to be looking at. It's just something really important for you guys to know about. But you can predict how reactive or unreactive an element will be based on where on this periodic table it's hanging out. If it's anywhere near the edges, very dangerous. Unless it's in group 18, then it's already happy. This is kind of the exception. Anything near the middle will probably be pretty stable and safe to handle. But that pretty much wraps up our lesson for today. So thanks for listening, guys, and hopefully that gives you all the information you need to know about periodic table trends.